I think it's already set. I mean, it should be, I guess. No, I think we were on Zoom. I mean, yes, should be okay because.
There are some people still making phone calls or whatever. I guess they will come. So, okay, then it's good reason to stay inside for the next 2 hours to have the rain passing by. So we are happy that Massimiliano will entertain us for some time in between, talking about precise predictions for the associated production of Higgs and W bosons with a top quark pair at the LHC. Please.
Okay, so thank you very much. Thank you for the organizers for inviting me to attend this workshop and to give this presentation. What I'm going to talk about is two specific relevant processes at the Large Hadron Collider, which is TT bar production in association either with a Higgs boson or with a W boson. So if we look at the standard model cross sections at the LHC, what we see is that there is this class of processes where a TT bar pair is produced with a W, with a Z, or with a Higgs, or even with a photon that range into this ballpark here. You see that basically the cross sections are more than a factor of 1,000 smaller with respect to the TT bar cross section. But still, these final states have been measured, and in particular, they are relevant for a deep understanding of the structure of the top quark interactions. So these processes, so in order to obtain precise predictions, of course, next to leading order QCD corrections are barely needed. So this is, of course, it's an audience which is quite, I think all of you know what does it mean to do next to linear order calculation. So I just show you just one slide just to remind you what are the ingredients that have to be combined. So here I have in mind just as to start with the production of a heavy quark pair. So we have 3-level amplitudes with 2 additional partons that enter next to leading order, 1 loop amplitudes with 1 additional partons that needs to be evaluated in the unresolved limits. That is when this additional gluon, for example, is soft or collinear. And then we have 2 loop amplitudes plus in principle, plus of course also the 1 loop squared, which do not which have the same Born level phase space, but contain all the singularities which typically usually are regulated by using dimensional regularization. So the fully differential computation to this cross section is crucial because typically analog corrections depend on the fiducial phase space on which the measurement is done. So what is the method that we use? So the method is quite well known. We proposed it together with Stefano Catani already in 2007. So the idea is very simple, and it's the fact that, for example, if you consider a colorless final state, like for example a vector or Higgs boson or more Higgs bosons, when you require additional jet activity, essentially the contribution to the cross section can be computed by doing a lower order calculation, that is an extra linear order calculation that we know quite well how to do. So basically, if you start from this point, then in the limit in which the additional radiation is soft or collinear, you will develop additional singularities which can be properly subtracted with a counter term. And then you have to re-add the contribution, which is obtained with a perturbative computable function that here is called H, with the Bohr level cross-section. This function essentially contains the virtual contributions after subtraction of infrared singularities plus collinear and in principle also large angle soft radiation if the process for example, includes heavy quarks, as we will see in a moment. In general, this equation is valid up to power corrections that depend on the cut that we apply on this ratio Qt over Q, where Q is the transverse momentum of the system on which we are triggering. So the structure of these functions can be obtained from all-order resummation, and now it's even known up to n-cube. Indeed, the method has been also applied for also at n-cube for colorless particles. But this is I mean, I'm not going to talk about this. So how do we get this counted? How do we derive these functions that are needed? These are derived by using resummation. And in particular, we start with the well-known approach, which dates back to Parisi-Petroncio and Collins-Soper-Sterman, that has been reformulated later by our group. And essentially, the functions here, essentially what you have to do, you have to work in impact parameter space, and you describe the small transverse momentum limit of this colorless system. Suppose that this is, for example, a dilepton pair, by using perturbative computable functions that are the collinear functions, which describe radiation at scale 1 over b. And then there is a pseudo-Four factor, which contains a soft and flavor-conserving collinear radiation. And then there is a hard function, which essentially contains the virtual. Of course, you can get a perfectly equivalent picture of this small Qt process by using soft collinear effective theory. Okay, they are perfectly equivalent. So the situation becomes more complicated once we replace this colorless system with colored particles, and in particular heavy quarks. Okay, so once you replace this dilepton pair here, the difference between these two diagrams is just that I'm replacing this dilepton pair with a QQ bar pair, where Q is a heavy quark. I have in mind the top, or for example also the bottom. Then in this case, the picture is more or less the same, but there is an additional perturbative ingredient that needs to be taken into account, which is this delta factor, which accounts for purely soft radiation. So the heavy quarks do not lead to additional collinear singularities because they are heavy. Okay, so the mass regularizes additional final state radiation, but they are colored. So the pattern of soft radiation is more complicated with respect, for example, to Drellian. So in the Drellian, you just have initial state partons. Here you have initial and final state massive partons. And the structure of the singularities you have to add also large angle soft gluon emissions. So this factorization picture has been developed by us and also equivalently also in soft collinear effective theory. And essentially, it leads to some modifications of the Qt subtraction formula. Basically, what you have to do, you have to modify the subtraction counter term because, as I said, there are these additional soft singularities that, however, can be described by ingredients which are fully known up to next leading order, in particular the soft anomalous dimension gamma t. And then there is also a modification to this function here, which does not enter the singular limit, but it enters the finite cross-section at zero transverse momentum. And this object essentially is controlled by these soft emissions that need to be computed and that we have computed. And we have put out our paper early in January this year. So here I'm not entering into the details, but just to give you a flavor of what one has to do in order to understand the structure of these additional soft singularities, you can start from the iconal factorization. So you have 4 partons, 2 initial state partons two heavy quarks in the final state. So you can start from the standard equal current. However, this current will contain additional singularities, which are initial state singularities, which are already accounted by the calculation. So you have to subtract them, okay? So the way we proceed is to define a suitably subtracted soft current such that this object here essentially describes only the additional large angle soft gluon radiation that is missing to correctly capture the physical picture there. Okay, so note that this approach is different from what is done in soft collinear effective theory. So this is not exactly the soft function that is computed in SCET. And the reason is that in SCET, typically, these calculations are done by defining objects which are not physically finite. Okay, they typically use, they need to use rapidity regulators, which have to be consistently used also to compute the corresponding beam functions. And it's only when adding beam soft functions and everything that the rapidity divergences cancel out. In this picture, we use it's fully equivalent. So don't get me wrong. I'm not saying that what we do is better than what they do in SCET, but this quantity here is fully finite and it can be computed on its own. It does not require any rapidity regulator in principle. So, okay, so then of course this calculation here is trivial. We did it already 10 years ago. What is less trivial is to do it in next to next to linear order. So in next to next to linear order, you have several sources of soft contributions. You have, for example, a soft QQ bar pair, which also contributes, and the soft limit of three-level amplitudes when there is a QQ bar pair has been described already by Catania and myself many years ago. Then there is also the case, of course, when you have two soft gluons, and again, the soft factorization formula is known, and then you have a soft gluon emission at one loop order. You have to properly construct and integrate the subtracted soft currents for these three contributions. And in the end, you will get the additional poles, if you want, that are needed to cancel the singularities, and one over epsilon singularities in the calculation, and to complete I mean, if you want, the full calculation. So that's all for the technical part. If you are interested, I can also discuss further this point. So this is done, okay, and it is finally implemented into our numerical problem that is called matrix, and I'm very happy to see that nowadays people are using it, and even, I mean, yesterday there was a talk on which was showing results obtained with our program, so I'm really proud of this. In particular, after a lot of validation work and efforts, now really TD-bar is in the public version of matrix, so everybody can download it and try it together with other processes, like, for example, three-photon production in the latest version. So, but this is not the subject of my talk, so I want to discuss the production of a QQ bar pair plus a color singlet. So what are the additional problems that we have in this case? So when the heavy quark pair is accompanied by a colorless system, the resummation and the subtraction formalism, of course, can be applied in just exactly the same way. Okay, so the colorless system does not change, it's colorless, so it doesn't change the structure of the singularities. And so basically, this was already done already 3 years ago to obtain for example, the off-diagonal corrections, analog corrections to TTH. However, the colorless system takes away momentum, okay? And so this means that the computation of the soft function is slightly more complicated than what we have done for QQ bar. This has been done by my collaborators, Devoto and Mazzitelli, and should be out soon. Then there is another complication that for important processes like, for example, TTZ and WWBB, which all fall into this class. There are 3 parton correlators which are non-vanishing and also contribute to the soft integrals. This is not the case for TT bar, TTH, and TTW. Then the only, yes?
When we have time to understand how the soft function would have a different correlation between TTW and TTZ, can you elaborate on why is that?
So the reason is that it's a quite technical reason. So the 3 parton correlators are vanishing when you have when you don't have axial couplings. Okay. So for example, TTX, they are vanishing. There is a theorem that has been proven by independently, I think, many years ago by Seymour and also by Chacon, which really you can really prove that these objects vanish by essentially by they cancel out with the complex conjugate. To be very naive, but this is what happens. So in TTW, the only Bohr level channel that you have is quark anti-quark annihilation, and then in that case, even if you have axial couplings, there is only one color structure that enters, and you can show that they are also vanishing. But in TTZ, there is also the gluon channel, and when there is a gluon channel with axial coupling, in general, they don't cancel. Okay, it's a rather technical reason. So I was saying, okay, so we have basically everything ready if you want. And of course, the important, crucial missing ingredients are the 2-loop amplitudes. Okay, so the 2-loop amplitudes for these processes are 2 to 3 amplitudes with different mass scales, which are really at the limit of what can be done nowadays. Okay, there is progress. Our friends in the loop community are working hard to get, and they get continuous progress, but this is really at the limit. Okay, typically we have results in the leading color approximations. So basically what we try is to circumvent this problem. Okay, so we try to use approximations for the 2-loop contribution to obtain, and this is what we have done with my collaborators for TTH, WBB, and TTW. So I will start with TTH. So TTH is, of course, it's a crucial process. Okay, the LSE, as you can imagine. Okay, it has already been established a few years ago, and it directly allows you to extract the top Yukawa. Currently, the uncertainties are still relatively large. If you look at the Atlas and CMS summary plots that are taken from the 2 Nature paper published last summer in 2022, you see that we are of the order of 20%, but still this is fine with, so it means that with current experimental precision, I mean, the next to linear order, if you want, is still sufficient. But if you look ahead, the experimental precision is expected to get down to the 2% at the end of the high Lumi LAC. And while current predictions, which are based on QCD plus electroweak and next to linear order plus resubmission, have an uncertainty which is of the order of 10% or larger. So to push down this uncertainty to the 2% level, definitely NLO is needed. And so we have, with our collaborators, with my collaborators, we have done first the off-diagonal partonic channels already in 2020. So what we do here in this work is to approximate the missing GG to TTH and QQ bar to TTH amplitudes by using a soft Higgs approximation. Now I'm going to describe. Okay, so we are all familiar with what happens when we have a soft photon or a soft gluon emitted in a high energy process. Okay, in a high energy process, when you emit a soft photon, essentially the soft photon has a large wavelength, so it's not able to see the details of the high process. It only sees the external charges, and then you get the formula, which is essentially the equal factorization formula. So what is maybe a bit less known is that an analogous formula holds for the emission of a soft scalar of heavy quarks. So if you have a soft scalar, if you replace these lines here with the heavy quarks, and you replace the photon with the Higgs, with the light, very light Higgs, you can show straightforwardly at level that you can construct an analogous current, which is obtained by summing factors like this, where m is the heavy quark mass. Here I'm taking heavy quarks with all the same mass, m. And there is basically the coupling is given by the Yukawa coupling, if you want m over v. Okay? So this formula, you can really derive it by doing a back of the envelope calculation. So the nice thing that we have discovered is that this formula can be extended to all orders in QCD. And essentially, the physical picture is that the current does not change. Okay, what we know is that in QED, the equal current is not affected by higher order corrections. But in QCD it is, and you have higher order corrections which are known up to loop order, which are non-abelian. What happens for a scalar is that if you want, the Higgs behaves rather in an essentially abelian way. So there are no corrections to the current when you look at the higher order QCD effects, except for an overall factor, which is universal and which is actually related. This function is related, can be extracted from the soft limit of the scalar form factor of the heavy quark, which is known, and this is the explicit expression. So you can derive this formula by using these arguments, or if you wish, one can derive it by using Higgs low energy theorems. Yes.
That will change the number of final state. Is this formula still valid in that limit, or is this limit not contemplated?
So what do you mean? What is the?
So you say that it factorizes completely in terms of what there is there at board level, and then there are a regular factor which is
yes.
This regular correction could have a dual.
But that would be real correct. Here I'm considering virtual. Okay, I'm looking at so I'm considering. I mean, at the multi-loop amplitudes where there is a scalar, and then I'm saying that the amplitude factorizes into this form, where this factor essentially is just a renormalization of the Yukawa coupling, if you want. You can think it like this. So again, if you want, I mean, I have some additional slides in the backup on this. So we have done several checks to convince ourselves about this formula, and of course we can do many checks at one loop order. Okay, at one loop order we can compute exactly the amplitudes, and we can test this formula. So we have tested it, of course, numerically with open loops for TTH to check that indeed the formula works perfectly. We even tested it numerically with Recola up to one loop in the case of 4 top production plus a Higgs, and we have seen that it works. So this formula that I have just presented can be useful to cross-check future exact calculations of QCD amplitudes, but it works in the limit in which the Higgs is soft. Okay, so then the natural question that you can ask is, well, but I mean, the Higgs is 125 GeV. Is it realistic or not? So can we use it or not? Yes, remarkably, we have, I think we can use it, and now I'll try to convince you about it. So let me start with again with the formula that we are using. So the QT subtraction formula can be written like this. So all the ingredients in this formula are available except the virtual, which is included into this calligraphic H function. So let me isolate exactly what we don't have. Okay, What we don't have is the virtual, which, if you want, is at n loop order, where n here will be 2 in practice. What we need is, with some subtraction of the infrared singularities, the interference of the 2 loop with the Bohr. Okay, this is exactly the term that we need. So I can define this function here in this way, and I can isolate it into the cross section. All the rest, I know it. Okay, so here I use the infrared subtraction of singularities, which is customarily used, for example, in Becker and Neuber papers, if you wish. So there is a z to the -1 factor, which depends on the subtraction scale. So the subtraction of the singularities, of course, is arbitrary. Okay, you can always subtract a finite piece. So it depends on a subtraction scale. So all the other terms are known. So, for example, the 1 loop square is known. I can compute it. Okay, I can take open loops or Recola if you wish, and I can get it. So I just need to approximate these coefficients here. So in order to start with, so we will start with next to linear order, because there we have an exact result. So we have used our factorization formula to construct approximations of these hard virtual coefficients H1 and H2. So first of all, since the X is not at all soft, in order to use the factorization formula, we have to introduce a mapping to define the phase space. Okay, this you don't need it in the strictly soft limit, but if you want to compute an approximated form of this coefficient starting from a physical event in which you will have a top, an antitop, and a physical X, you need to decide to tell me how do you reabsorb, if you want, the momentum of the X. To this purpose, we use the so-called QT recoil prescription that we introduced several years ago with Catani, Ferrera, and De Florian. So with this prescription, the momentum of the X is equally reabsorbed by the initial state partons, leaving the top and antitop momenta unchanged. So all the amplitudes are computed with open loops, and of course, to construct our factorization formula, we need the 2 loop amplitudes after factorization, which are the TT bar amplitudes, which are fortunately available from Chacon and collaborators, so we use them. This is the setup that we use for the numerical results, an MPDF 3.1, and as a central scale, we use the typical scale that is used for these processes, that is twice the top plus X masses divided by 2. So let me start with, of course, the first thing you can do is to check how it works in linear order. Okay, so at linear order, you can check how things work, and you see that, well, it's not working so well. Okay, in the GG channel, you are off by a factor of 2 if you use this approximation. And in the QQ bar channel, you are off by 10%. Okay, however, so at first sight, we are not very happy, but still, these are absolutely linear order predictions. So in our calculation, we will actually need to approximate the H1 and H2 coefficients, which are obtained by normalizing to the linear order. So actually, we compute effectively K factors. Okay, it's just we do a weighting if you want. It's similar to what we do when you apply the large and top approximation. Okay, typically you rescale with the exact Born and you compute effectively a K factor. So if you do this, this effective reweighting, things, as we will see, work way better. And actually, our result will depend on the scale at which we subtract the infrared singularities, which is set to the invariant mass of the final state system. So let's go quickly here. So if we compare the hard cross-section exactly in the gluon channel and next to linear order, what you see is that basically we are off by 30% in the gluon channel and by 5% in the quark channel. So things are definitely better. So our approximation with this definition that we applied on the H coefficient only and next to linear order capture the bulk of the effect, okay, because we are off by 30%. Of course, it's rather clear that the quality of the approximation is not very good overall. So it will depend on how big is what we are going to approximate. If the impact of what we are going to approximate is large, then there is no way to get a precise prediction. But if what we are approximating is small, then it will work out. And indeed, what we find is that the next to next leading order, we get that the hard virtual contribution with the soft approximation is of the order of 1% of the linear order cross-section. So even if I get this 1% very roughly, the error that I'm doing is not terrible, okay? So, however, the important point is to, since we want to give predictions to the experiments, we want to make a solid statement, we would like to so we have spent a lot of time really in trying to convince ourselves of what are the uncertainties of what we are doing. So here, unfortunately, I don't have so much time left, but quickly going through it. So basically, by studying different recoiling prescription, by studying different choices for the subtraction scale, we convinced ourselves that if we take essentially the deviation that we see at next to leading order and we multiply by a tolerance factor of 3, we are quite conservative. And then finally, the uncertainties that we get are combined linearly between the quark and the gluon channels. This, due to the smallness of this two-loop contribution that we have estimated, boils down to an uncertainty which we estimate to be of the order of 6 per milli. Okay, which is way smaller than the residual theoretical uncertainties. So these are the numbers that we get. So we get an extra linear order, the effect is 25% at 13 TeV and 44% at 100 TeV, and next to next we get 4% and 2% with a significant reduction, as you can see from here, of the perturbative uncertainties. These in bracket are the uncertainties due to the QT subtraction systematics plus estimated as we usually do in matrix, plus the dominant. So this QT systematics is way smaller than the residual uncertainty from the soft approximation, which is, as I said, is 0.6%. So this is the cross section as a function of the energy, and you can see that this small stripe here corresponds to the uncertainty due to the soft approximation, which is subdominant with respect to the residual perturbative uncertainty. So let me quickly go to the second process and more recent calculation that we have completed. So TTW is among these TTV signatures is special, okay, because it involves both electroweak and top sectors, and it is at the same time a signal and a background to TTH and for top production. It's particularly relevant for new physics searches. So since the top quark quickly decays into a W and a B jet, the signature is characterized by 3 W bosons, which provide an irreducible source of same sign dialecton pairs relevant for many BSM searches. So, it is special compared to other processes because the W can only be emitted by initial state light quarks. So there is no gluon channel at linear order, as I mentioned before. So, and it is important because in this moment of depression in particle physics, there is a consistent excess in this process, starting from the observation, okay, at ATV, that is measured by Atlas and CMS. So they have measured consistently an excess of events, which is always at the level of 1 to sigma with respect to the standard model prediction. So this calculation was highly demanded by particularly by the top working group to us. Okay, so we got quite some pressure, but in the end it was a pleasure to work on this. So so theory predictions are essentially based on extra linear order, QCD plus electroweak plus some soft Galois resummation. And actually the current theory reference is the so-called FX prediction which is obtained by combining next to linear order with multi-jet merging. So we don't have the virtual, so we have constructed and tested two different approximations for the two loop amplitudes, and here I describe them very quickly. One is still a soft approximation, so we can use a soft approximation for W emission with momentum K and polarization epsilon to express the TTW amplitude in terms of the QQ bar to TT bar amplitude, which is known, and this is the formula that one can use. And another approximation that we have used is to start from the W+4 part on massless amplitudes, which are available from Samuel Abreu and his collaborators, and to use what my chairman has proposed many years ago, a so-called massification procedure. So the idea basically is the following. If you, from a massless amplitude, you can construct an approximated form of the massive amplitude by essentially using some universal perturbative ingredients, which encode essentially, if you want, the step between the collinear poles, which are regularized as 1/epsilon in the massless limit, 2 logs of the heavy quark mass. Okay, of course, this is an approximation, but one can try it, and actually it was successfully applied to WBB by my young collaborators in this paper here. So we thought to apply it also to WTT. So we use exactly the same approach as I described in the TTH, yes. So we have to define appropriate mappings to evaluate to use the two approximations consistently, and so we use all the 3 level and 1 loop amplitudes that are obtained with open loops and Recola. So these two approximations are based on two completely different perturbative ingredients. One is the QQ bar to TT bar to loop amplitudes, which has been recently recomputed by Mastrolia and collaborators with a fully analytical computation. But however, we still use our implementation from Chacon and collaborators. And then there is, as I said, a completely different result, which is the W+4 part on massless amplitude, which is massified according to the procedure that I have very quickly described before. So this is the result. So the first thing is to look at the next to linear order. So how does it work at next to linear order? So what we see is that we study the hard contribution to the cross-section at the inclusive level, and by applying cuts on the transverse momentum of the top quarks. Why do we do this? Because we expect that if we require hard top quarks, then both approximations should work better and better. And this is indeed what you see, it happens. So both approximations provide a good estimate of the exact one loop contribution, because we are talking about percent level here. The soft approximation undershoots the exact result, while the massification overshoots it. So there is a clear asymptotic behavior towards the exact result at IPT. So now we can go to the next order. And at the next order, remarkably, both approximations, which, as I said, are physically completely different, are not too far from each other, okay, these approximations. So basically, what do? We take, for both approximations, the soft and the massification, we define the uncertainty by taking the maximum between what we obtain by varying the subtraction scale around the central scale, which is the invariant mass of the final state system, and twice the next to linear order deviation. So the philosophy is that if a next to linear order, my approximation works up to 10%, I give to the next to next an uncertainty of 20% at least. Okay, this is the philosophy. So I do this for both the soft and the massification result. And what you can see that by doing this, we get, so the blue and the red uncertainties, the bands, they overlap. So our best prediction is obtained as an average of the two with a linear combination of uncertainties. So, of course, this procedure, you may tell me that it's arbitrary. Okay, nevertheless, what you see is that the differences between these two results is in the ballpark of 10–20%. Okay, so it means that we are able to estimate our two-loop contribution at this level of accuracy, which is quite remarkable. I would like to remind you that analogous calculations that have been done by our competitors, Chacon and collaborator, always use leading color approximation for the virtual, which has the same accuracy, roughly. So we are not too far from I mean, I think we have a quite a good control of this result. However, unfortunately for this process, the virtual is large. So it's completely opposite to TTH. So the contribution of the two-loop virtual that we find is 6 or 7% of the next to next to linear order cross-section. Okay, so I try to conclude. So this means that this will have an impact, non-negligible impact on the final uncertainty. Okay, so these are our results. So next to linear order, the K factor, the increase of the cross-section is about 50%. Then we have an impact of the analog corrections of the order of 14–15%. So the scale that we are using is, as I said, twice the top plus the W mass divided by 2 as a central scale, but one can choose other scales. And by looking at, now I don't have time to enter into all the details, but by looking at these different central scales, we end up with a procedure to estimate the perturbative uncertainties, which is the following. We take m/2 as central scale and we symmetrize the uncertainties. So we do basically like this, and this is our final perturbative uncertainty. This is supported by the fact that the next to next linear order, we don't see large contributions from new channels which are opening up. Okay, so the analog corrections are dominated by virtual and real corrections in the Quark-gluon channel. So we think that this procedure is sufficiently conservative. And these are the numbers. So the numbers have a final uncertainty which is of the order of 1.8% from the soft approximation, which is however still way smaller than the residual perturbative uncertainties, which is at the order of 6–7%. So these numbers here include all the subleading, all the electroweak corrections, also the subleading terms that were included in current benchmark predictions by the MADGRAPH group. And now I can show you the comparison with the data. Okay, so basically the comparison with the data shows that the discrepancy remains at the 1–2 sigma level. So the inclusion of analog corrections significantly reduces perturbative uncertainties, but the result is fully consistent with the numbers that have been used in the recent 2 or 3 years by the experimental collaborations, which are based on the FX prediction. So this is Atlas and CMS, and here you see our results where these orange uncertainties are due to the soft to the approximations that we are doing on the two-loop field. Okay, with this I can conclude. So processes in which a TT-bar pair is produced together with a vector or Higgs boson are crucial to characterize the top quark interactions. And so there is a high demand from the community for analog predictions. So what I've tried to convince you is that the method that we are using, QT subtraction, is fully suitable for this kind of processes. And in particular, now that we have computed the missing soft contributions that are required to implement our method fully for this class of processes, we have applied the method to these two processes, TTH and TTW. So for TTH, the approximation that we are using only for the virtual is based on a soft Higgs factorization formula that I have presented for the first time at the next linear order. And for TTW, we have used two approximations, a soft approximation and a massification procedure that give very nicely consistent results within their uncertainties. So together with WBB, these are the first calculations for 2 to 3 processes with massive colored particles at this order. So analog corrections are moderate and lead to a significant reduction of perturbative uncertainties. And in the case of TTW, for which, as I was saying, there was a high pressure from this particular from the experimental community to have these predictions, there is still room for new physics. Okay, the discrepancy remains, is not covered by analog predictions. Thank you very much.
Okay, thank you very much for this very nice presentation. Questions or comments to Massimiliano?
Thank you for the nice talk. I have a curiosity concerning the TTW. You have shown that at next leading order, the massification tends to overshoot and the soft to undershoot. I was wondering if there is any argument to expect you're at next loop, or there is no way to expect that.
So, I mean, there is no argument to the reason to expect this. Okay, this is just, if you want, observation. So at 2 loop, I show you what I get. Okay, I mean, the pattern that you see at next to leading order is consistently observed at next to next. So that's why we expect. So our prediction is defined as. Of course, I don't have the exact low result, but if I next to leading order, I see that my 2 approximations are consistent within a few percent, I have, I think, good arguments to say that if next to next, my calculation gives me this blue and red that are differing by only 15%, if you want, that my exact result should stay in between. Of course, with uncertainty. So you can always tell me that you are not satisfied. I mean, we try to be conservative, but it's of course it's an arbitrary procedure.
Actually, I would have a number of questions, but I'll try to keep it more about the first part in which you were sort of giving the general picture. So when I'm referring to the calculation in which you have the soft current and you subtract the collinear singularities, right? So if this was purely virtual, which is possibly a different situation, you would have 2 options. You are subtracting the collinear from the soft, but you could equivalently subtract the soft from the collinear, and which is, for example, in the subtraction that we do is our preferred method. Would it have been possible, or do you think there is an obstacle? So going back into the collinear factors and taking away the soft from them.
So, I mean, okay, in principle it's possible, but I mean, here it's really try to find the simplest strategy. So you have a process, you understand fully a process in which there is no color in the final state. So then you know exactly what your ingredients are. So then you say, I replace my final state with a heavy quarks. So these heavy quarks have soft, large angle contribution. So why not to try to describe these soft wide angle contributions by not having to recompute the beam functions? Because the problem is that you have done a lot of work. You want to recycle it as much as possible. That's the strategy. So,
okay.
I mean, starting from scratch, one could of course, probably also go in your direction. But
that's clear.
This is what we did 10 years ago.
Quickly, just about this calculation, which is not finished by Mazzitelli, in which you say it makes a difference if you have a color neutral momentum being carried away.
Yes, it's not that this is finished. It's just that it's not published, but we have the results.
why you mean that in the original calculation of the soft current they were actually using total momentum?
In the paper that we have published in January, there are basically, I mean, you have to look at the various contributions. There are, in particular, the most difficult contribution is the one in which you have color correlations between T3 and T4, which are the heavy quarks. Okay, so then this is computed numerically. We didn't manage to do it analytically. So to simplify the calculation at that time, because I mean we wanted to get to the end, okay, and to simplify the calculation, we have used the transistor momentum conservation, assuming that there is nothing else.
Yes.
Then we have realized that actually these integrals is actually only this. So it's only a part of the calculation that needs to be extended, because basically all the other pieces you can recycle them from. You can use exactly what you have for heavy quark. But for these contributions, you have to. So you can do it more generally but once we understood how to do it numerically, then you have to. So then Mazzitelli and Devoto have basically build up a library that hopefully they will publish soon, in which this is fully encoded.
Okay. And then just a quick observation, which is not about your talk. So I am always impressed or puzzled by the announced idea that on such observables there will be a 2% experimental uncertainty at some point. Because, I mean, TT bar H, there are channels in which it becomes 10 jets with 4 B jets.
No,
just the combinatorial uncertainty.
This is an issue. I mean, this is the plot that I've shown is on the High-Lumi record. Okay, you can tell me you don't trust it. No, you are right. The problem is the systematic. So it's at the moment, I would say it's really difficult to anticipate such a reduction. Also because it's the systematics that you have to understand, but it's sort of a leap of faith. Let's put it like this.
I have a quick question to the next to last slide with your TT bar W results. So what's the value of the top quark mass that you have used there?
So here we are using 173.2, if I remember correctly.
Okay,
but,
so did you ever check what happens if you vary the top quark mass by ±1 GeV, say, on this on the slide where you compare to experiments? I mean, we could then see probably which direction the theory result moves. I think it was the next to last slide before your summary. Next. This one, yeah. So basically, if you have a ±1 GeV variation of your theory result, it would give you an idea.
If you lower the top mass, then I expect the cross section.
Right, the cross section should rise, so it gives you a bit of an idea on what
we didn't study.
That would be interesting to see, because it gives you an idea on the parametric dependence. Let's call it this way.
Oh, that's true. You are right. Yeah. Yes.
Okay, thanks. Did you have any? Okay, good. Then let's move on. Let's thank Massimiliano again.